So we're going to pick up off of pH indicators. And so one of the things you need to remember when you're looking at a titration, any sort of titration, is that the equivalence point is when the moles are equal, right? But in real life, you don't have a magic indicator that says, ding, 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 moles are equal, right? I have neutralized all of my acid with that base I added. Congratulations, you can finish now. That doesn't happen in real life, right? So in real life, we have to go off of other things. We have to set up situations where we're going to stop, hopefully close to where that equivalence point would be. And so what we're doing with pH indicators is we need to use pH indicators who change color very, very close to where that equivalence point would be. Okay? It's never going to be perfect. There's always going to be some error in there, right? But if you change your color right on where that has a drastic rise in its slope, remember that? Your pH curves, where it's pH versus the amount of titrant you added. And it has that part where it just shoots up really fast, right? Okay. If you change color somewhere on this line here, this is typically going to be very close to your equivalence point. And so you can use that as your equivalence point with a relatively small amount of error. Okay? Now, one of the more popular pH indicators is phenolphthalein. This works very well for strong acids, strong base titrations. Works for weak acid, strong base titrations typically. It's pretty rare for this not to work for those. It is a weak if a weak acid has a very small Ka. You okay over there? Okay. There's more power outlets like here and there. Okay, you can see everything? Okay. It looks like I put you in the punishment corner. Here, sit in the corner, face the wall. Okay. Anyways. All right, so phenolphthalein may not be the correct choice if you have a very small Ka, because your endpoint would happen way before you would hit your equivalence point. Okay? And so you'd be very far off then. You would need to use an indicator with a higher pH indicator range in that case. The weak base, strong acid titrations typically require indicators that would change color at lower pH values. And so you would need something that doesn't change its color up at the 8.4-ish, 8.2-ish region. You need something that changes its color down in the less than 6, right? And so that's how you end up choosing these things. So for the titrations that involve the weak acids or weak bases, typically it's best to go ahead and choose an indicator that's going to change color within 1 pH unit of the equivalence point. Okay? And so for strong acid-base titrations, that color change can actually be within 2 pH units of your equivalence point. And that has to do with, remember where we looked at that graph and we had the different weakest acid, weak acid, and then strong acid? And it had a larger shift, faster shift that happened. So that equivalence point has more leeway when you're looking at a strong acid with a strong base. Okay? It has a larger pH change at that equivalence point area. The weak acid is going to have a shorter pH change at that equivalence point area. And so you need to be within plus or minus 1 pH to be able to catch that. So these are the pH ranges of selected indicator color changes. So here we have that methyl orange. This is going to be a red color at pH 3.2. This is a 4.4, it'll be a yellow. This is bromocresol green, 3.8 to 5.4. Those are where it has the changes in color that are clear to your eye, that you can tell the difference. Okay? Anyways, there's phenolphthalein, by the way. 8.2 is the actual colorless cutoff. Most people, though, can't see that at 8.2 because of the very light pink color to it. Clear to, very light pink. And so typically what you end up getting is up here. Now, note that this actually fades back when you exceed pH 10. This is a kind of common mistake with phenolphthalein. People think that they can just go ahead and be pink when it's basic, period, with no caveats to it. Okay? And people will throw phenolphthalein in, and they'll have a bunch of extra base, and then it goes back to clear, and they're like, what the hell's going on? This is why. Actually, the phenolphthalein above pH 13 will actually gradually fade back to colorless. And yeah, this is the range that starts turning right here. Okay. Okay. Anyways, this is one that you would use for even weaker acids that would change up in the near 10-ish range. Okay. All right, so this would be an interactive. You have an interactive that you can play with and see how that works out, okay? Now, note again that, what we're looking at is when you have an endpoint, that's when you stop titrating. That's when your indicator tells you, hey, you should stop titrating, okay? You have an equivalence point. An equivalence point is when you actually have an equal number of moles of the acid and base, and they neutralize each other completely, right? These are two slightly different things. When you're titrating, you try to set your endpoint to be very close to your equivalence point. Okay? But this is always going to add error. So select an appropriate indicator from table 17.1 for the titration of a weak acid. This is the weak acid with a strong base. The expected equivalence point of this titration is 9.3. So our equivalence point is 9.3. What do we want our endpoint to be? What would be the ideal situation for our endpoint to be? (9.3), right? We'd want to end at our equivalence point, right? But do we ever get the ideal situation? Is the roads perfectly flat? No. Are you perfectly symmetric? No. No. We never get ideal situations, right? And so the reality is we just don't have any indicators that are going to be able to be matching every single pH that we want to end all the time, right? And so what we need to do is we need to choose an indicator that's going to have its endpoint occur within plus or minus 1 of that pH, right? And so we would go to that table, we look at the table, and we go, what has an endpoint that's the closest to that pH that our equivalence point is at? Okay? Or it should be at. Well, which one? Yeah, these are really only the two options you have right here. And the phenolphthalein is definitely closer, right? Yeah. And so phenolphthalein would be a pretty good choice, okay? The azurine yellow could also work because we do have a color change that's 10.2. It's reasonable. Like, that's just a bit after. And so that would work pretty well, okay? Now, when do you actually want to change stop, by the way, for these? So if you're using phenolphthalein, when do you actually want to stop your titration and go, oh, that's the equivalence point? Do you want it to be super dark pink? Or do you want it to be super light pink? Typically you want it to be light, but that's because you would have an endpoint here that's up in the 8s. This time you'd actually want to go to where it's noticeably pink. You don't want to go all the way, but you can actually be sloppy with this one, it would work well. You'd actually get better results, or more accurate results, I should say. Okay? And so this one, you'd actually be better off to getting a noticeable pink color, rather than just almost nothing. Okay? This, on the other hand, the azurine yellow, so we look at this color range here. This is yellow going to red, right? So the colors that would happen as we go along here would be yellow, orange, and then red, right? what color would we want to actually stop at? We're already going to be overshooting our pH, aren't we? So we actually just want it to not be yellow anymore and then stop, right? As soon as it's not just pure yellow, as soon as we start seeing any hints of red or orange in it, we'd want to just stop there, okay? And this would be that normal phenolphthalein where we just stop when we see any color at all. Because we want to try to skirt the edge of it, right? We don't want to go into the middle of it. Is this making sense? So you see, you can actually get better results by using the depth of color as well, okay? And if you were doing this with spectroscopy, like a visible light detector, you could get a very exacting measurement and standardize this, okay? But with your eyes, you're going to have difficulty. All right, now, which direction would this go if you screw up? If you screw up with phenolphthalein, what's going to happen? Whoops, added a bit too much, it's a bit darker pink. Am I going to get a bad result? No. Actually, phenolphthalein was a great choice because it gives you a lot of leeway, doesn't it? It's going to be very noticeably pink and it'll be clear before that. You really can't screw up and become inaccurate because of a little bit of screw up, okay? You really have to mess this up really badly to become inaccurate. Now, azurine yellow, on the other hand, alizarin yellow, excuse me, what happens if you over-titrate a bit? If you get it to red, you're way over, aren't you? Yeah, because it was only the very edge of this that would have worked, okay? So it's better to have it where it's centered around it than it is to be where it's on the edge like that. So if you designed this lab to do a standardization, like a Coca-Cola factory or something, then yeah, this would be the better choice, the phenolphthalein. This would be the worst choice. But you can get the very edge. So the solubility product constant, this is KSP. You may have been wondering, hey, I've seen equilibriums, Dr. Clausen, where we have things dissolving. Where's that stuff? Guess what? We're getting there. Okay, so we're now going to look at solubility. Does everybody remember solubility? What does it mean to be saturated? If I'm saturated, do I have any of it in the solid form? So technically, saturation is right on that border, okay? So I could have a crystal in the solid form. I probably won't be able to see it if I'm actually on the saturation. But if I'm oversaturation, what happens at oversaturation, where I've put extra solid after saturation? Yeah, it'll just go to stay solid, right? It's not going to go in solution. And so this is actually what the solubility constant is going to tell us. It's going to tell us how much of this would dissolve in a typical solution. Now, when we look at K's, equilibrium constants, what do we do with solids? If I have a solid on one side of my equation, what do pure liquids and solids do in the equilibrium expressions? Yeah, it's like nothing. We don't put it in, right? Technically, it's called unity, but you guys don't really need to know a lot about unity yet. If you want to go learn more about that, that's analytical chemistry. Okay. So these solubility products, well, these are going to be for saturated solutions. We're going to have these equilibriums, or equilibrium constant for that equilibrium of a solid dissolving into a liquid, typically an aqueous solution. Okay, you can do these for other things than water, but by far and away the most common one is water, because water is the universal solvent on this planet, right? So these are always going to have the solid on one side, and the solid is typically, by designation, put on the left side, the reactants. And then it's going to be in equilibrium, and it will be the dissociation of that solid. And so the dissociation of that solid typically breaks apart into the cation and anion for a salt, right? Now, notice in these reactions, these equilibriums, all the time, what happens? This is a heterogeneous equilibrium, isn't it? We're always going to have a solid on one side, and then aqueous solutions on the other, different phases, and then we're going to have a neutral compound going to an ionic compound. Can everybody see that? Okay. What does that mean for you? You never divide by anything with these solubility product constants. They're always just one line. The stuff on the bottom would have always been the solid over here. And so you never need to do anything with it. Okay? Pretty nice, right? Yeah. Now, the one thing that you're going to go, oh, Dr. Clausen, this thing gets clearly easier, is that keep in mind that solids can break apart into more than one item. Remember your Van 't Hoff factor? Yeah. So we can have, for example, two iodides right here, which means that the iodide concentration will be squared, right? Okay. And so that does add some complication to the math. By the way, this is again called a heterogeneous equilibrium. Why do you think it's called a heterogeneous equilibrium? The two sides are different phases, right? Yeah. So you have different phases. So it's heterogeneous because one side would be a solid, right? So if you have any unreacted reactant here, it's going to be a solid. On the other side, we have a aqueous dissolved in solution. What does this look like? Well, this looks like this right here. So this is a precipitation reaction. What we're getting is we have lead, nitrate, and potassium iodide. The lead and iodide combine together and give you a salt that has a very low KSP. It's doesn't dissolve well. Okay? On the other hand, the nitrate and potassium, those are both very soluble. Okay? And so this then precipitates in solution and ends up falling out of solution eventually. And that's where we see this right here, which is the precipitate, right? Does the precipitate have to be gathered in one area nicely like that? No. It can also look like a snow globe, right? Or milk. Okay? Milk would also be a precipitate. Milk just has its precipitate suspended. Anybody seen really old milk, set it in the fridge too long? Has all the stuff fall out, and it's like clear, gross stuff on top. That's the precipitate falling out. Okay, so your KSP expression for your barium phosphate is this right here. And again, this would be your KSP expression. Notice the third power here comes from the coefficient, right? And remember, that's just that same K equilibrium expression, products of reactants, powers of coefficients, right? Okay, just in case you forgot. So remember, in these equilibrium expressions for KSPs, the solids and liquids do not appear. They go to unity. We don't have to deal with them in this expression. The concentration, again, needs to be raised to the powers of their coefficients. Please remember those. Do not forget those. I know that we've spent a long time not using that because acids, bases. All right, so these are some of the solubility product constants at 25 degrees Celsius. If you have a very small number like this right here, what do you think that means? You remember the solubility rules back last semester? Gen Chem 1? Those solubility rules back in Gen Chem 1, they were actually just a really simplified version of this, okay? So if you're something that's normally considered soluble, you're going to have a value here that would be 10 to a positive power, meaning it mostly dissolves when you put it in solution. Very little of it will stay as a solid, right? For example, you already knew this because sodium chloride does not always all dissolve, does it? When you make salt water, sometimes you get a little salt at the bottom, don't you? Okay? And so right here, these numbers would be typically for stuff that is what's considered usually insoluble. Okay? Now, is an insoluble thing actually completely insoluble? No. These numbers tell us some of it does dissolve, right? Remember, these numbers are these two multiplied together. If they did not dissolve, then that number would be 0, right? Closer to 0, the less soluble you are. Larger the number, the more soluble you are. And so these typically are what is referred to as insoluble, but as you see here, they are not completely insoluble, and under certain conditions, they can actually become more soluble. Anybody have any questions about that so far? If I see a number like that, by the way, what does that mean? Is that very soluble? Would I expect to see a lot of that salt dissolve in water? Or would I expect to see that aluminum hydroxide stay as a mostly solid? Okay. What's going on, guys? Come on. So a number very close to 0, 10 to the negative 33 is pretty close to 0, right? That number means that very little of this goes in solution, okay? Because remember, these are going to be the ions that would be dissolved in solution multiplied by each other, right? Okay. So a number like this means very, very, very little of it would dissolve in solution. Again, these are all what would be normally considered insoluble salts, okay, from Gen Chem 1, meaning almost none of it dissolves, right? A number like 10 to the negative 3, though, means this actually dissolves to some degree. So if you were to put this in water, you would find cadmium and fluoride, okay? You wouldn't find a lot of it, but you'd still find it. Okay, these are some more KSP values, and you can see here, these are, they can go very, very low and be very, very insoluble. None of these are going to be ones, notice that 10 to negative 70, by the way. Ooh, You haven't seen numbers like that, have you? All right, so none of these would be considered particularly soluble, okay? The really soluble stuff would have a positive number here, right? And they can be very, very soluble, by the way. So a saturated solution of iron 2 sulfide is going to contain 4 times 10 to the negative 10 molarity of iron 2 plus, 4 times 10 to the negative 10 molarity of S2 minus. Let's calculate the KSP for iron 2 sulfide. Okay, so this is just a straight up equilibrium problem, isn't it? Okay. And so we take these numbers, we're going to write out our KSP expression for our dissolution of the iron 2 sulfide. Now, this does require you to review some concepts that you started learning back in chapter 2, and you have used basically since then. But if you don't remember them, that is the naming conventions and writing out the formula for an ionic compound, right? So iron 2 means it has an iron with a 2 plus charge, right? And then the sulfide has a negative 2 charge. And so you have a 1-to-1 relationship, 1 iron to 1 sulfide. When it breaks apart, it's going to give you 1 iron and 1 sulfide, right? That relationship means the KSP equals the concentration of iron to the power of 1 times the sulfide concentration to the power of 1. Okay? Now we go ahead and take these numbers, we plug these in. They're the same number because it's a 1-to-1 ratio. By the way, this also told you it's a 1-to-1 ratio right here. Them being the same equilibrium concentration meant they had to be a 1-to-1 ratio, right? And so we plug those numbers in, and we get 1.6 times 10 to the negative 19. Anybody have any questions? Did I lose anybody? Nope. Okay. Now, this is just straight up equilibrium problems, right? Yeah. Hopefully everybody's like, God, Dr. Clausen, just get over it. I'm done. Okay. Now, the KSP, this gives me a measure of a compound solubility again. All those rules and everything that I taught you about solubility in the previous chapters, those still holds true. This is just a better way to look at solubility. It is a more complete understanding of solubility. Okay? So the lower KSP's values are going to be generally indicative of a lower solubility, but only when you look at two compounds that have essentially the same stoichiometry. One of the complicating factors is if you look at this table here and try to compare these KSP numbers, remember that these are to the power of their coefficients, right? If we look at the formula for an ionic compound, where's the coefficient located? So let's look at equilibrium real quick. 3 here, right? Coefficient. That's the power down here, right? Okay. If I looked over here, do I see a 3? I do. Where does this 3 come from? The 3 over here. Because we break it apart, right? We have to make 3 of them. We have no other choice. When we break it apart, there's 3 of them. This one here, there's 2 of them, so there's 2 over here, isn't it? Okay? So if I look at this table here, this has a powers of 1, doesn't it? If I try to compare this to this right here, well, this is 4th order, isn't it? It has 4. It has a power of 1 on the AL and a power of 3 on this one, doesn't it? If I plug the same concentrations in these two numbers, I'm going to get wildly different KSPs, aren't I? Can everybody see that? And so what that tells me is if I try to compare something like, for example, the barium carbonate right there, silver chloride right here, these I can compare very easily, okay? Because they have the same powers, right? And this one right here is a little bit more soluble than this one. Cool. If I try to compare something like this BAF2 here with something like this, which is a 3, power of 3 here, it's going to be a bit more complicated. Because again, I could be multiplying an extra factor in there, right? I'm going to have an extra power in there that I'm not accounting for right now. So the lower KSP, though, does generally indicate a lower solubility. Okay? But you do need to take into account the stoichiometry. If you match the stoichiometries, the lower KSP is just less soluble. Okay? Smaller KSP number, less soluble. But stoichiometry does play a factor in it. The KSP values, for example, Ca calcium S sulfide, magnesium sulfide, these are comparable because we have 1 cation, 1 anion for both of these. And so we very easily compare the KSPs. If we try to compare them for something that has a 2 or 3 on one of these, and we're going to have multiple, so we have different powers, for example, 2 cations and 1 anion for this one, these are not going to be directly comparable. Okay? You're going to have to calculate the concentrations at equilibrium to compare them. So let's use the KSP values in that table 17.2. We'll compare the relative solubilities of copper chloride, copper bromide, and copper iodide in water at 25 degrees Celsius. And so we look those values up. Right here, we see that copper chloride is going to give us 1:1 ratio, right? Copper bromide, same ratio. Copper iodide, same ratio. And so are these values comparable? Yeah. Yeah, we can compare those. They have the same powers, don't they? Same coefficients, same powers. So we look at these KSPs here. We have a 10 to the negative 7, 10 to the negative 9, 10 to the negative 12. So iodide is the least soluble, isn't it? The 10 to the negative 9 is the next one, and the 10 to the negative 7, that's the most soluble. And so we went ahead and figured that out. So the KSP and solubility, these are not actually the same thing. The names do make them a little bit easy for people to confuse though, okay? Remember, the solubility is the maximum amount that can be dissolved in a solution, right? After that, everything you put in is just gonna fall out of solution, okay? The KSP, on the other hand, is the equilibrium that's going to be made, right? The KSP does not actually tell us whether it will have any solid or not, okay? It's related, but is not the same thing at all, right? The KSP is going to be calculated from the KSP expression. The solubility is actually the amount of substance that's dissolved in a saturated solution. It's the amount that you would get in there before you start seeing solid fall out. The molar solubility is the number of moles of a substance that can dissolve in 1 liter of solution. Literally molar as in molarity, solubility, right? So right here, we go ahead and see an example of this being calculated. And so here we have an ice problem. Yay. I told you, everything can be done with ice problems, right? If you don't know what to do, write an ice problem. Okay, so right here again, I've set up an ice problem. I have calcium hydroxide going to its dissolved ions, right? Okay, and so I have lots and lots of calcium hydroxide. Excess, I'm gonna have solid at the bottom of this, okay? And then I start with 0 calcium and 0 hydroxide. Again, my ice problem would tell me I would reduce this by some amount. This I would get the same amount because there's a 1-to-1 ratio, right? This one I'm going to get 2 times that amount because again, that's a 2 right there, isn't it? So it's a coefficient 2. For every calcium I get, I need to get 2 of these hydroxides, don't I? Okay. Now, at equilibrium, why is this value empty? It's solid, yeah. I don't care, do I? I don't need it. The other thing is, this is excess minus x, so excess minus x is still excess. But no, it's just not important in these problems. I never need to worry about the solid, because I'm not going to use it. This one's 0 plus x, so x, 2x here. So I go ahead and write out my expression. My KSP equals the concentration of calcium times the concentration of hydroxide squared. I'm going to go ahead and substitute these x's in, so x and 2x. Now notice this 2x is squared. Now, don't get scared and confused. Even though I'm squaring and putting powers on these things now, they're all multiplication powers, okay? And so I don't have to actually do anything really complicated with multiplication powers. So I just take these and square the internals. So that's 4 times x squared, right? And then 4x squared times x. So that's 4x cubed. Is everybody okay with that? Okay. Now, the molar solubility for this is actually just going to be equal to x. So if you have excess here, then that's just the x, which is the 1-to-1 ratio one, right? Literally the concentration of the 1-to-1 ratio with this overall salt, okay? And so my x here equals, I will go ahead and solve for x, so KSP divide by 4, and then I take the cube root, right? By the way, I have never used the number root in my entire life. Do you know how to do this without using that on your calculator? You can also take it to the 1/3 power. So to the power, you know, a little caret, and then 1/3. Okay? That's how I've always done it. I've never done it the other way because it's hard to find that stupid button. Easier to just take everything to the powers. So this is actually true for any ionic compound that has the same stoichiometry, if it's an A and B2. So if you have 2 anions, 1 cation, this is always true for that. Okay? You can actually solve these down into formulate if you'd like. I would not actually recommend memorizing the formula to try to do that way. It's a really dumb way to do it because you end up memorizing like 10 different formulas when you could have just easily solved these within about 10, 20 seconds. Okay? But if you do have trouble with the math and solving these out each time and setting up the ICE problem each time, you can actually use these formulaic responses. Okay? So calculate the molar solubility of F2. The KSP of BaF2 is listed in table 17.2, of course. So if we're calculating the molar solubility, how much of the solid do we have? Lots and lots, right? Excess. So we set up our ICE table. Again, it's going to be the solid breaking apart into its components, which are the cations and anions. Don't forget the polyatomic cations and anions, by the way. We'll get to those and have more of those examples coming. But there's no reason this had to be a monoatomic, right? This very easily could have been nitrate, okay? Okay, and so we go ahead and have this broken apart. We start with 0 here, plus x gives us x. Is everybody clear on this? Does anybody have any questions on how to set up ICE tables at this point? Okay. Yeah. If you do still have questions on how to set up this ICE table and you get lost on it, please come in and talk to me, okay? Very, very much so. It really is just something that if you practice it and actually do it a few times, you'll learn how to do it and it'll be like riding a bike, right? Very, very quick and easy. So we're going to write out our expression. Again, it's going to be the concentration of Ba2 plus times the concentration of F minus. Don't forget your coefficients are your powers, okay? I know that we've been away from that for a bit, about a chapter and a half now, but keep that in your head. So those numbers are going to get substituted with these x values, so x and 2x squared. So we're going to then solve that equation. So our KSP is the value from table 17.2, 1.84 times 10 to the negative 7. We're going to go ahead and divide that by 4 and then take the cube root, right? Or the 1/3 power, whichever one you do. That's going to give us the molar solubility, which is x. And so we go ahead and do that. And we get 3.58 times 10 to the negative 3 molarity. That is the molar solubility. Note, by the way, just to make sure that you have this broken in your head, because it's a very common mistake that students make, this KSP value is not the same as the molar solubility. Okay? Not the same number, not the same. All right? Okay. Everybody's very clear on that, right? Fantastic. So the solubility of barium nitrate here is 27.5 grams per liter. Let's calculate the KSP of the barium nitrate. You knew that was happening, didn't you? As soon as you saw me go one way on this problem, you went, Dr. Clausen's going to make us go the other way too. Because I always do, don't I? All right. So let's start by converting the solubility into a form we can actually use in a nice problem, which would be molarity, right? Now, how do we get this in molarity? Well, how is grams related to moles? It's related through the formula weight, isn't it? The numbers on the periodic table. So we go ahead and add those together. 1 Ba, 2 nitrogens, 6 oxygens. That gives us 261.338 grams. That's the amount of weight that would be there for 1 mole. And so we go ahead and put grams on the bottom, so the grams cancel. We'll be left with moles on top over liters. And that gives us our molarity, which is 0.1052. Okay, so now that we're doing an ice problem with a solubility that's going to be coming out of this thing, that solid right here, you can always just ignore this, by the way. I know I keep putting excess minus x and such, but you don't actually have to do that. That's just for clarity, bookmarking purposes, okay? And because I already had a table set up and copy and paste works. So, you know, you can actually just ignore this. When I used to be in your shoes, I would just put a bar through here and move on to the next one. So this is 0, 0. You get the idea. Anybody have any issues? Fantastic. So we write out our KSP expression. Again, this is a x and a 2x raised to the second power. That's going to give us a 4x cubed. We go ahead and substitute this in this time because we have a concentration here for this barium nitrate. Now, one of the caveats and a place people commonly make mistakes here is this. What exactly is that concentration of? Is that the concentration of nitrate? No. It's the concentration of barium with 2 nitrates, right? Okay. So barium will have that same concentration, won't it? Because it's a 1-to-1 ratio. The nitrate, on the other hand, is going to have 2 times that concentration, isn't it? See that? Okay, and this is why you always do these as whole numbers, by the way. It makes your life so much easier if you have something like this. Okay, so we plug that in. That's actually going to be our x. So this is going to be that concentration we figured out, 0.1052. This will be to the third power, so we take the third power. We multiply it by 4, and that gives us our KSP. And that's that value right there. Anybody have any questions? Very good. Okay, remember the common ion effect that we started all of this off with? Feels like it's been a while. Okay, if we have a common ion, if we increase the concentration of that common ion, it's going to push our equilibrium, just like Le Chatelier's principle said, right? Okay, so the common ion effect is going to be the suppression of a weak electrolyte's ionization by the presence of a strong electrolyte containing an ion in common with the weak electrolyte. The common ions are going to reduce the solubility of ionic compounds. So, for example, the molar solubility of silver chloride is 1.33 times 10 to the negative 5 molarity. This is the equilibrium right here. What would happen if we added 0.2 molarity of sodium chloride to this? Well, sodium chloride is a strong electrolyte. Anybody remember what strong electrolyte means? It means it dissolves completely in solution, right? So it would not be in equilibrium if it's a strong electrolyte, right? It goes all to ions. So adding 0.2 molarity of sodium chloride means we've added 0.2 molarity of chloride. Hey, remember the ice problems? There's that initial concentration, right? The initial concentration of chloride would be 0.2, isn't it? If we initially have a 0.2, what's going to happen to this equilibrium? Well, we increase the concentration of the chloride, and it gets pushed towards the left, the solid, doesn't it? So this is going to reduce this right here's KSP. It's going to reduce its solubility. It's going to make it harder for this to dissociate, isn't it? Or another way of saying that is it's going to go backwards towards the silver chloride much faster. Okay? Anybody seen the silver mirroring reaction? No? Or the, have you guys done any of the, where you use different, detect the ions that are in solution? Have you guys done that yet, or are you guys doing that in the near future? Okay. near future then. You put different salts together, and you get solids here and solids there, and it tells you if you have silver or. Okay. We'll do that in the future then. Okay. So again, the additional chloride shifts the equilibrium back towards the silver chloride. So let's calculate the molar solubility of silver chloride in a solution that's 0.2 molarity NaCl, compared with the molar solubility of silver chloride in pure water, that solubility being this number right here, which is 1.33 times 10 to the negative 5 molarity. The KSP of silver chloride is in that table, 17.2 that was listed before. So again, we're going to set up an ice problem for the equilibrium we're going to be playing with. And so silver chloride going to the silver cation and the chloride anion. They're all 1-to-1 ratios, so this makes the problem a little bit easier. Now, we don't have any silver starting, do we? But we have 0.2 molarity of a strong electrolyte. And that has chloride it's going to make. So the chloride actually starts off at 0.2 molarity. And so we put that into our ice problem. This is going to again be minus x plus x plus x because they're 1-to-1 ratios. And our final equilibrium values are x and 0.2 plus x. Okay, so again we have our KSP expression, concentration of silver, concentration of chloride. This equals the KSP value from table 17.2. And that is this value right here. Now, we plug these x's in, so x and 0.2 plus x. Considering this number over here that we're equal to, are we going to get a very large number for x here? Probably not, right? So we can actually use that same 5% rule we've been using, where we go x is less than 5% of this value. So we're just going to ignore it and assume that that's not important, okay? And that'll let us duck and avoid our quadratic formulas. Okay, and so this is going to give us x times 0.2. That KSP, that's equal to 0.2x, so we just divide 0.2 over, and that gives us our value for our KSP, which is 8.85, our x, excuse me, which is 8.85 times 10 to the negative 10. Now, that solubility, that number is actually that number right there, isn't it? We've just figured out the solubility. Another way of thinking about the solubility, it's the number that would have to go to hit equilibrium between the solid and the ions, right? Because when you're in equilibrium between those two, what does that mean? What does that mean to be in equilibrium between the two? Does equilibrium mean I'm never going to see one of the species? If I'm in equilibrium here, should I ever see any solid? I actually kind of have to, don't I? Because if I'm in equilibrium, it means I'm going both directions at equal rates, right? So if I'm at equilibrium between solid and liquid, it means I'm going to see a bit of both, aren't I? I may see very little of one, but I have to have the possibility of seeing one, right? So this equilibrium in many ways actually means I've set up a solubility, haven't I? Yeah. And that solubility limit is going to be at that tipping point at an equilibrium, okay? So that solubility, that molar solubility numbers, they meant that I've established an equilibrium, haven't they? Yeah. There you go. Okay, so I have x here. That's my equilibrium, my molar solubility at that equilibrium. And so what we notice here is that that's actually a lot less than this number here, isn't it? Yeah, we've actually reduced the solubility by 5 order, haven't we? Yeah. Big difference. Common and effect, very effective. So the effect on pH of solubility. Anybody ever heard of Flint, Michigan? No? Okay, about 10 years ago, there was a city that they changed their water supply to a new lake reservoir. And it caused all the lead pipes to start leaching lead into the water and made the whole city's water supply poisonous. They couldn't drink it. Yeah. And it didn't get fixed for, God, it was like 6, 7 years that took them to finally fix it. Yeah. They actually turned the city around afterwards, and they've done a much better job, but it was a total fucking disaster. This is why that happened, by the way. Okay? Their new source of water is more acidic, and so their lead pipes became more soluble. Okay? So the pH of a solution will affect the solubility of an ionic compound that has a basic anion. The acid is going to neutralize the basic anion. This will shift the equilibrium to the right, increasing the solubility of the compound. Essentially, we're stacking two equilibriums together when we're looking at these. So remember, acid, H3O plus, reacts with base, OH minus, right? So if one of our products would be something like OH minus, which is basic, right? Then an acid is going to react that away, isn't it? What happens when we lower the concentration of one side? Causes the equilibrium to shift towards that side. Yeah. So we're going to shift and become more soluble, aren't we? Because we're removing this species right here. That's turning into water. Okay. Can everybody see that nicely? Fantastic. Okay, so again, this is going to shift that equilibrium towards the products, towards the solubility. This is also true for anions that are weak bases. So let's determine which of the following compounds will be more soluble in an acidic solution than in a neutral or basic solution. This is actually true all the ways you can imagine this would be true. If you react away one of the soluble components, you're going to increase the solubility. Okay? Okay, so this right here is the mercury hydroxide. If we added acid to this, what would happen? So when this dissolves, what does it make? Yeah, and hydroxide, you got it. OH minus. Is OH minus base? Does it have basic properties? Oh yeah, it's the base, right? And so if we put an acid in there, it's going to react away one of the products, isn't it? That means that an acid would make this more soluble. Everybody said okay? Okay. How about copper bromide? Is bromide, which would be one of the products of this, is that a acid base? Does it have any basicity, acidity? So that's the anion of a strong acid, isn't it? Meaning it has no acid-base properties. Okay? It's neutral. And so it's actually not going to do anything. Right? How about this one would give fluoride, wouldn't it? Okay, so is fluoride basic or is it not basic? There's another way to look at these things. That's to look at the anion and say, if I added an H plus to that, would that give me a strong acid or would that give me a weak acid? If it gives you a weak acid, then it's basic, isn't it? If it gives you a strong acid, then it doesn't have any basicity. Okay? And so H2O, weak acid, right? HBr, strong acid, no basicity. HF, weak acid. Okay? That means that's basic. That means if I add an acid to this, it's going to increase the solubility. Okay? So precipitation, let's talk about the Q versus K. Anybody remember Q at all? The reaction quotient, right? We want to write up an equilibrium expression, but we don't know if we're at equilibrium. And we want to see if we're at equilibrium. The solubility product constant, KSP, this is going to be a measure of your compound solubility again. So when several ions are present in solution, you can actually determine which compounds are going to be precipitate by comparing the KSP to the reaction quotient. The reaction quotient will tell you if you're below, at, or above equilibrium, right? Which direction you have to go. So the reaction quotient for a heterogeneous system is very mathematically similar to the solubility product constant. However, the KSP is the product of the ion concentrations at equilibrium. Q is going to be the product of ion concentrations under any conditions. It could be at equilibrium. If Q is at equilibrium, it would be K, right? But under any other conditions, Q is not K. So right here we see Q. Again, it's the same thing as an equilibrium expression. It's just may not be at equilibrium. So Q is less than KSP. The solution is not yet saturated. You can add more solid to it and it will still dissolve. Okay? Q is equal to K. The solution is saturated. It's at equilibrium. If you try to add any more solid, you're going to have it precipitate. Okay? If Q is greater than KSP, the solution is actually past the point of saturation. Remember supersaturated solutions where we talked about those? They'll eventually fall out of solution. That'd be a supersaturated solution, okay? So this is going to have excess ionic compound. This will precipitate from the solution until Q equals KSP. Have you guys done any crystallizations in Gen Chem yet? Where you put something in like an ice bath and it starts precipitating? Okay. Now, that's actually what you're seeing. So you're lowering its temperature, that lowers the KSP, right? You end up with Q above KSP. Eventually, it may take a while. You may have to scratch the side of the flask to speed it up a bit. But what will happen is Q is going to shrink as you crystallize that product until Q equals KSP. Okay? So this right here is again the solubility equilibriums again, and we can see here Q is less than KSP. We can go ahead and increase Q until it reaches KSP, and that will give us equilibrium. If Q is greater than KSP, we're going to precipitate until we reach Q is equal to KSP. We'll reach the solubility equilibrium. So equal volumes of a solution of 0.0015 molarity AgClO4 and a solution of 0.0015 molarity NaCl are mixed. Will the AgCl precipitate? Okay. So how we figure that out is we take these ions, we plug them into our, guess what type of problem this is? Nice problem. It's a nice problem. Damn near everything is a nice problem. Okay, so again, we are going to calculate the Q and see if this is above, greater than, or if it's equal or less than the KSP. If it's greater than the KSP, this means this is going to precipitate, isn't it? So we go ahead and set up our Q. These are equal AgCl, so 1 to 1. So what we're going to do then is we've mixed these two solutions, right, in equal volumes. So what that means is that our initial concentrations of these is going to be, for Ag, it's going to be that 0.0015 divided by 2, right? Because that's half of our total volume. Okay? And then we're going to have half of this for our chloride. And these end up with the same numbers, because we made these problems mathematically easy, so nobody would get confused. So 0.0015 divided by 2, again, half of this number. 0.0015 divided by 2, half of this number. Again, I selected this one for my Ag because that's Ag, right? It's a 1 to 1 ratio. I selected this one for my chloride because that right there is the chloride, and again, 1 to 1 ratio. I multiply those two numbers together. I get 5.63 times 10 to the negative 7. That's my Q value. I don't know if that is at equilibrium or not yet, right? So what I then need to do is I need to look at my KSP value. My KSP value is 1.77 times 10 to the negative 10. That value right there is a smaller value than the value I have, isn't it? Okay. So what does that mean? That means that this Q value is going to need to go down until it reaches KSP. And that means my ions are going to join together to form silver chloride until I reach Q equals KSP. And this is going to cause precipitation. Now, when I look at precipitation again, does it have to have all the ions joined together at the bottom of the flask? No, ions can join together in the middle of the flask, the top of the flask, wherever, right? And that will cause them to float a little bit, and eventually they'll fall out. So again, we're going to look at the selective precipitation of ions now. So in cases where several ions are present in solution, one or more ions can be selectively precipitated, i.e. removed from solution, by using a reagent based on different solubilities of those compounds. For example, if a solution contains both the silver and magnesium ions, the addition of HCl or NaCl is going to selectively precipitate the silver because the silver has a much, much lower KSP than the magnesium would. The magnesium, in fact, has no given KSP value because this is a sparingly soluble compound. Okay? So your magnesium chloride would mostly not precipitate. You'd get very little, if any, magnesium chloride as solid. Whereas the silver chloride, most of the silver is going to precipitate out as you add this NaCl. Okay? Anybody have any questions? Okay. And you're going to use these principles at some point in this semester to design a separatory technique where you can separate these different ions. All right. So suppose you have a solution containing the barium 2+ and magnesium 2+ ions. Which of these salts could you add to selectively precipitate barium? So we're looking to separate these two things, right? We want to separate barium out. So right here we have the sodium carbonate, right here we have the sodium phosphate. Okay? What are we looking for to try to separate these things out? We're going to look for the KSPs, right? Specifically, we're looking for the KSPs of barium with these anions, right? So barium carbonate, barium phosphate. Do we want a high KSP or a low KSP? Now, the lower our KSP, the better it precipitates, right? So we want to find the one that has the lowest KSP with barium. So we look at our table. Barium carbonate, KSP of 10 to the negative 9. Magnesium carbonate, 10 to the negative 6. Okay, those have a decent separation. This is less soluble here than the magnesium carbonate. And so you can mostly precipitate out the barium before you precipitate out the magnesium. Okay? So that would do an okay job. We look at the phosphates now, right? And so the barium phosphate, 10 to the negative 23. The magnesium phosphate, 10 to the negative 24. That's not a big difference, is it? Not compared to the other one. This was 1,000 times difference. This is like a 10 times difference, isn't it? So this would not do as good of a job separating these. You'd end up with quite a bit of magnesium phosphate with your barium phosphate. Okay? Yeah, you'll get more barium phosphate than you will... You'll get more magnesium phosphate, actually, than you will barium phosphate in this case. Because this is the lower number, isn't it? Okay. Anybody have any questions about that? All right. Fantastic. So qualitative analysis. This is where you actually use this to do a qualitative analysis to tell you what salts do I have. Does anybody remember the difference of quantitative and qualitative analysis? Don't worry, I thought you might not. So there are two types of basic chemical analyses. There's qualitative analysis and quantitative analysis. Qualitative analysis is going to test for the presence of qualitative, yes, I said qualitative. Test for the presence or absence of your chemical species, regardless of their amounts. It's actually what qualitative means, right? It's a quality of something. Is it a square or a circle? Is a person present or absent? Okay? Yes, no. Right? Blue, red. Qualitative, right? Quantitative analysis is going to determine the quantity or the amount of a chemical substance present. Are there $10.12 in my account? Are there $10.13 in my account? Okay? I'm looking for a number, right? Not a yes-no answer. Okay? Does everybody get the difference there? Okay, fantastic. All right, so let's look at the systematic identification of metal ions. We can do this via precipitation using these rules that we've just talked about. So what we'll do is we'll have a mixed system of different metal ions. Reagents will then be added via specific orders to separate and identify metal ions in the solution. 5 different precipitation reactions are performed to identify 5 specific groups of metal ions. Now remember that when we look at the periodic table, groups have properties, right? And so what we're doing is we're using the group properties of these metal ions. So precipitants from each group can then be further analyzed to determine the identity of your metal ions present. And so right here is a typical flow chart for this separation. And so here we have an aqueous mixture of our cations. That's our initial one. It has a bunch of different cations in it, okay? So we add HCl to this until we stop precipitating stuff, okay? So we get precipitant. That precipitant is going to be things like silver, lead, and mercury, okay? And the reason that these come out is because the chloride is going to cause those to become very insoluble, isn't it? Yeah, it has very low KSP. Okay. On the other hand, you'll have remaining cations. Now, these cations, this HCl here, the reason this is used is this hydrogen here, this H+, this is going to cause anything basic to become more soluble, isn't it? See that? And so we're getting just the chlorides out because we're using HCl. Instead of like sodium chloride, okay? All right, and so the next step here is going to be, we're going to take this solid, separate it out. There's a few different ways you can do it. Anybody know some different ways to get rid of a solid? Leave behind the liquid? Anybody done filtration? Haven't done filtration? You made coffee? Okay, when you make coffee, you're getting the liquid down and you're leaving the solid behind, aren't you? That's filtration. The other way would be a centrifuge. I think you guys are actually doing that this week. Or maybe it's next week. But I know you're doing it very soon. So the next step is we then take that solution, absent the precipitate, which we've collected and removed. We're then going to add H2S. These are going to be under acidic conditions. Notice we've actually already made this acidic, right? With the HCl. So this is being smart and using those conditions. So the next thing that's happening here is we now have sulfide, don't we? So anything that's not soluble with sulfide, that's insoluble with sulfide, is going to come out as a solid. And that's these species right here. Any remaining cations will be soluble in the presence of sulfide, right? Or they'll be ones that make a basic anion. So the next step is to add with still the H2SO4S, the sulfide in the presence of sulfide, we're going to go ahead and put base in, okay? And so we're going to neutralize our acid, and we're going to establish basic conditions. This is going to give us the things that are insoluble when they have hydroxide present, isn't it? See that? And so these are the ones that are insoluble with hydroxide present, right there. Okay, that will be our precipitate. We again get our solvent, our solution, the stuff that's still dissolved. We move that over. The next step is we would add carbonate or we would add phosphate. One of the two. They actually work pretty interchangeably. You may have noticed that the things that were insoluble in carbonate are mostly insoluble in phosphate as well. They're pretty analogous, actually. So the next part is these are the species we will then precipitate. Now, if you don't precipitate anything here, the stuff that doesn't precipitate from carbonate and sulfate, or phosphate, excuse me, and all these other ones, these are very, very select group. Do you guys remember your solubility rules at all from General Chemistry 1? No? Okay, so in General Chemistry 1, you had a section where you talked about half a chapter on the solubility rules. If it has sodium in any anion, it's soluble. Doesn't sound familiar? Okay. All right. So anyways, that's actually what you're seeing right here. Okay. So these cations right here, they're soluble with essentially any anion. It doesn't matter what anion I put in. These are soluble. Okay. And that's why they're left behind in solution. All these different anions can't make these insoluble. They're just soluble. Okay. Notice what group they're mostly in. Lithium, sodium, potassium. They're group 1, aren't they? Yeah. This is ammonium. It's the only one that's not in group 1 because it's a polyatomic, right? And those are the ones that would have been in your solubility rules as just soluble, period. They're always soluble no matter what you put in with them. The addition of HCl solution is going to precipitate the chloride salts of the sodium, lead, and mercury. If no precipitation forms, then it's actually reasonable to conclude that none of these three ions are present in the sample when you've added the HCl to get the insoluble chlorides. Now, these groups here, please be careful. Yes, these groups tend to be similar cations in the periodic table, okay? Meaning, for example, down here in this group, those are almost all group 1 on the periodic table, right? But these groupings are groupings of, this is group 1 right here, okay? This doesn't actually refer to the periodic table, group 1, 2, 3. This refers to this group right here, this group here, this group here, this group here. Okay? First thing you try to get, second thing you try to get, third thing you try to get, fourth thing you try to get. Does that make sense? I know that the terminology makes this really annoying. Okay? Because they called periodic table rows groups, they called these groups as well, and they actually have quite a bit of overlap. But they're not synonymous. Okay? They're not the same things. These are actually not group 1 cations in the periodic table. They are group 1 cations in reference to the first thing that comes off because they're insoluble chlorides. Okay? And you always want to do this in this order because you're acidic. This requires acidic. This is basic. If you do this, you'll get some of these coming out as base. Okay? Okay. All right, so it's if you do that group 1 insoluble chlorides, if you don't get any precipitate, then it's actually reasonable to say that I don't have the presence of those. And this is how you can test, for example, do I have lead? Do I have mercury? Do I have silver in that solution? Okay? And this is the typical how you test for like lead, by the way, is you would do this test. If you have precipitate, you filter it out, you go to the next step, and you can later go ahead and run tests on that filter, okay, on that solid that you collected. What time is it? Oh, okay. Thank you. Okay, so we'll talk about group 2 on Friday. Please check out the video of that, okay? We'll have the exam on Tuesday. And I believe next week is also evaluations. Okay? I'm going to have you guys sit down and do evaluations for 15 minutes in class, because otherwise I get one evaluation for the entire, and that's it. And it's always the person that hates the professor, right? Yeah, because the people who like it are less likely to do it. But it's not about hate or like, it's about, I actually would like to know if you guys would like something covered more, if there's any things you guys want from this course. It would be helpful.